Chapter 2 of this course is all about functions and their graphs. So if you were tired of solving all of the equations in Chapter 1, congratulations. We have a bit of a break in Chapter 2 before we get back into it in the rest of this course. Because we're going to go over all of the things that have to do with functions and their graphs. Today, however, is mostly just a highlighting day. I would follow my color coding of highlighting if you want to be like my notes. So we've got all the markers in the bucket. I would make use of all of the colors, hopefully maybe in the way that I'm using them as well, because I'm going to use that color code pretty much throughout the course for these particular things. Also, there's like no examples in the notes, so we're just going to highlight the first 2 pages of your notes, and then we're going to go to the whiteboards and actually do the practice problems. So it's a very not sitting down day. Congratulations. All right, first things first, when we're talking about functions, we have to go even further back, and we have to talk about a relation. All functions are relations, but not all relations are functions. A relation is any set of ordered pairs. A mapping from an x to a y is considered a relation. In particular, though, they have names. The set of all first components of the ordered pairs is called the domain of the relation. Because I teach AP Pre-Cal as well, you're going to hear me call that the inputs a lot, because that is the name that AP Pre-Cal uses a lot for these things. They are the inputs for the function. They're what go inside the x's everywhere in the function. The set of all second components in a set of ordered pairs, second components, is called the range of the relation. And again, because I teach AP Pre-Cal and I have that language at the forefront of my mind, we're going to be calling those the outputs as opposed to maybe the second component. I will call them the outputs. They're what come out of the relation. Now, to make sure that a relation is a function, specifically a function is a correspondence from the domain to range, specifically that each element in the domain corresponds to exactly one element in the range. That is the formal definition here, but basically we're saying that we have to have unique input values, meaning the input values should not, cannot repeat. Your x's cannot repeat. It's maybe something you've heard before. That means that we have unique input values in this relation to consider it a function. Some more things, again, these notes are just kind of like information, and we're going to use them when we get to the whiteboards, but some more information for you, and I know we know a lot of this stuff. Function notation is used when you don't have x's and y's, but when a letter is used to refer to the name of the function, usually F, G, or H in either lowercase or capital. Please use the correct letter to talk about the function. And suppose that F names a function, we think of the domain as the set of the function's inputs and the range as the set of the function's outputs. The input is represented by the x. So again, that domain is our inputs. And this time, since we're in function notation, it's not that the y's are the outputs, but it's that f of x is the output. This special notation, f parentheses x, we pronounce it as f of x. Or if it was a g, you would say g of x, or g of 5, whatever number or letter is there. And it represents the value of the function at the number x, aka what we're plugging into the function. If you look at graphs, and I know we know this stuff because I've already asked you questions and you've given me correct answers here, but if you're looking at a graph and it has a closed dot, that means that the graph doesn't extend beyond that point and the point belongs to the graph. So it's an inclusive symbol. If there's an open dot, it's like the parentheses in our interval notations. The open dot doesn't extend beyond the point, and that point doesn't belong to the graph. So we don't include that number where the open circle is, or the parenthesis number is on a number line. We also know that in a graph, an arrow or lack of an arrow, open dot, or closed dot means that the graph extends infinitely in the direction of the arrow, because we know arrows aren't drawn on our calculators, but we know that they extend beyond. All things that we know. Something else we probably know but forgot about is the vertical line test. If any vertical line intersects a graph more than one point, then the graph does not define y as a function of x. So that question in Algebra 1 that they asked you, is this a function? You would take your pencil and move it across the graph and say, does it pass the vertical line test? It's the same thing. We're just saying that the graph, if it doesn't pass the vertical line test, it doesn't define y as a function of x. Getting a little bit further into the domain and range, because sometimes it's not just a set of numbers that you're looking at, it's going to be an entire graph. But the definition of domain and range does not change. The domain is the set of inputs, and the range is the set of outputs, which means you're going to be looking at the x-axis for the domain and the y-axis for the range. And so if you're given this graph, which is a semicircle, don't pay attention to the colors on my graph because it's actually the opposite of what I'm using. But for our domain, we would look at the x values on the x-axis where the graph shows up. So this semicircle only shows up between the numbers -4 and 2 on our x-axis. So that is our domain, and we can write it in two ways. We can write it in set builder notation, x such that x is between -4 and 2 with closed dots, or we can write it in interval notation with the brackets, -4, 2. The range, on the other hand, is the values of the y-axis where the graph shows up. So we have the lowest value at 1 and the highest value at 4, which means that the range is the y's, notice the letter change, such that y is between 1 and 4, inclusive with brackets, or in interval notation between 1 and 4. Does this all look like things we've done before? Fabulous. Some more things that you've probably done before is identifying the intercepts of a graph. Don't overthink these either. To identify the x-intercepts, you're going to look at the points where the graph crosses the x-axis. Woohoo! We express this in function notation by writing f of x equal to 0, meaning our outputs are 0. When our outputs are 0, we're on the x-axis. And since that x-intercept is where the outputs are 0, that's where we got that word, the zeros of a function, that we've used in many other classes. The zeros of a function are the x-intercepts because it's where the outputs would be equal to 0. Okay. Now there's other parts of a graph that we need to go over on the back. Again, some things that you may have already seen and or it's pretty logical. We're going to be describing how functions behave, and we're talking about the function themselves, so the outputs. How do the outputs behave? So without thinking too hard about it, how would you describe this graph? Curves up, goes up. We're going to use the word increases, or rises from left to right because it rises up. Okay, there's a big formal definition involving the x1s, x2s, f of x1s, and f of x2s. All you really need to know is that on this interval, the further you are to the right, the higher it goes. How would you informally describe the next graph? Decreasing. If informally we are decreasing, aka we are falling from left to right. Again, the further your inputs are would mean the outputs are lower or smaller. That's the formal definition that I didn't even print on here because it's not that important. And then if you were describing this last graph, how would you describe this? Straight. We're going to use the word constant, meaning it does not change. Or we can say that it is horizontal from left to right, meaning that no matter what x value you use, you're returning the same output value for the function. It is constant. It's exactly the same. Now, since we're describing the behavior of these graphs as they increase, decrease, or stay constant, and you will be describing this to me in maybe interval notation, like it increases from 1 to 5 or something like that, we can also talk about the extrema of the graph. Extrema is a fancy word that's talking about the maximums and minimums of a graph. It's just how you make those words plural, maxima and minima. A relative maximum, these extrema pieces are going to occur when a function changes its increasing or decreasing behavior. So if we change from increasing to decreasing, or from decreasing to increasing, we're going to have one of these maximum or minimum points occur. Okay? They're like hills and valleys, or peaks and valleys, right? We've answered questions about these for forever, but let's make it a little bit more of a formal definition. The function value f of a is considered to be a relative maximum if there exists an open interval containing a such that f of a is larger than f of x for all x not equal to a in the open interval. That's a formal mathematical definition of just trying to say it's a hill. Don't overthink it. It does have a very formal mathematical definition. All we're saying is that if we go from increasing to decreasing, we change the behavior of the graph, there's a maximum point here in the middle. Specifically a relative maximum, maybe not a global or extreme, but we are changing from increasing to decreasing. In fact, let's show that. Here's our increasing color, and here's the decreasing color. We change from increasing to decreasing, we create a maximum point. In the same way, a function value is a relative minimum of f if there exists an open interval containing b such that f of b is less than f of x for all x not equal to b in the open interval, which is a very fancy way of saying it's a valley. If we go from decreasing to increasing, clearly we had to go from down to up, we create a minimum point, a valley, if you will.
Is it kind of like that concave?
Yes, in AP Pre-Cal we talked about concavity. Concave points, how am I trying to describe it? Points of inflection is what you're thinking of, is when you change from concave down to concave up, or concave up to concave down. This one is like the highest point of a concave down section, that would be a maximum, or the lowest point of a concave up particular function. That's what you're thinking of. We don't need the concavity language in this class necessarily yet, so don't overthink it. We're just talking about the function's behavior. There is a little note that I want to put here because I got this question a million times last year. Because of this word open interval, when you're answering questions about increasing and decreasing or maximum and minimums, you're always going to use parentheses on your intervals instead of brackets. So on your homework today, when it's going to ask you to provide commentary on when something is increasing or decreasing, you're using the parentheses unless it's plainly obvious that there is a closed dot at the end of an interval. So err on the side of parentheses until you're absolutely certain it's a bracket, and that's only when you see a closed dot for these open intervals when it comes to increasing, decreasing, and maximums and minimums. Now, I know we've done almost 0 examples, and it's because most of this stuff is pretty familiar. This might be the only thing that's not that familiar for you, is our tests for symmetry, which leads us to even and odd functions. Don't overthink the symmetry, though. If we highlight these graphs in a very particular way, aka since this says symmetric about the y-axis, we highlight the y-axis. You see how you can just fold on the y-axis and one side of the graph fits directly on the other side? That's called a function being symmetric about the y-axis, or with respect to the y-axis. And all it means is that you can change the sign of the input values, keep the output values the same, and you've created both sides of your graph. Similarly, if we're talking about a function that is symmetric with respect to the x-axis, again, highlight that x-axis, and you'll see that the top would fold right on top of the bottom. So it's as if we took the output values and flipped them over, which is why you leave the inputs the same, but you change the outputs. The last one is called being symmetric with respect to the origin, and I'm going to zoom in on this one because it's harder to explain on a TV, so I'm going to show you on my iPad. But what it means for being symmetric about the origin in practice, it means that if you put like a pin right in the origin and you spun the graph around, like watch, I'm going to try to do this where you can see it, not on the TV, but on my iPad. So let me come stand over here. If I do this and then I spin it, doesn't it look the same? That means it's symmetric about the origin. So on your paper, you can put your pencil right on the origin and spin your paper around. And if it looks the same as when you started, that means that it's symmetrical about the origin. But in practice, in reality, what that means is we've switched the sign of both the x and the y. So notice that we have 2 negatives that have shown up in our new coordinate points that we can use symmetry to find. Now these symmetries, these 3 types of symmetries, lead us to 2 more definitions of functions and how we can categorize them. 99% of functions are neither even nor odd. But there's very specific type of functions that are considered to be even or odd. And I'm not talking about the leading coefficient or the degree of the polynomial. It's It's not what I'm talking about. This is a different kind of even and odd. An even function is defined to be that if you plug in a negative x, you get out the exact same thing that you had before. This is the definition that you would use. Now, if you plug in a negative x value and get out an exactly same y value, that means that we are actually symmetric about the y-axis. So it actually goes with this graph right here. So we should be able to fold even functions along the y-axis and see what they look like. But if we're solving this analytically, what it's telling us to do is plug in negative x, get out same y. We want to plug in the opposite input and be able to get out the exact same output, which is what that coordinate point tells me. Opposite x, comma, same y. Now an odd function, here's what's nice about this. An odd function tells me that if I plug in a negative x, I should get out the opposite y. So I need something that has both a negative x and a negative y. Which of your three graphs had both a negative x and a negative y? The origin one, which means odd functions are symmetric about the origin. If we were to plug in a negative x, we would get out the opposite function. So here's how I remember this. Odd, opposite, origin. That's so nice. Look at that. Odd, opposite, origin. The three O's go together. An odd function is symmetric about the origin and it returns the opposite output value. Wow, that's a lot of information and 0 practice problems. So let's go see if we can apply this knowledge that we would get out of our notes to the problems on the whiteboards with your team. You've already worked with them today, so you can go back to the same spot. You guys know my rules for collaboration at the whiteboard, so let's really work together to make sure we understand. Oops, I have this on.